The radius of curvature measures how sharply a curve bends at a point. It uses the circle that fits the curve most closely at that exact point, called the circle of curvature. In plain words, the radius of curvature equals 1 plus the square of the gradient raised to the power 3 over 2, all divided by the second derivative of y with respect to x. In symbols, this is written ρ equals open bracket 1 plus open bracket dy by dx close bracket squared close bracket to the power 3 over 2, all divided by d squared y by dx squared. An intrinsic equation relates the arc length along a curve to the angle the tangent line makes at that point. The tangent angle is usually called psi, and the arc length is usually called s. In symbols, the radius of curvature also equals ds by d psi, which is the rate at which arc length changes as the tangent angle changes. Let us work through an example. Consider the curve y equals x squared, and let us find the radius of curvature at the point where x equals 1. On screen, this parabola first appears as a flat two-dimensional curve, then the view lifts smoothly into 3 dimensions, showing the same parabola with the fitting circle sitting along it in space. First, differentiate the equals x squared with respect to x. This gives dy by dx equals 2x. Now evaluate this at x equals 1. This gives dy by dx equals 2. Next, differentiate again to find the second derivative. This gives d squared y by dx squared equals 2. Now find 1 plus the square of the gradient. This is 1 plus 2 squared, which equals 1 plus 4, which equals 5. Now raise this result to the power 3 over 2. 5 to the power 3 over 2 equals 5 times the square root of 5, which is approximately 11.18. Finally, divide this by the second derivative, which is 2. This gives ρ equals 11.18 divided by 2, which is approximately 5.59. Now let us check this against a different point on the same curve at x equals 0. Here, dy by dx equals 0, and the second derivative is still 2. So at x equals 0, 1 plus the square of the gradient is just 1, and 1 raised to the power 3 over 2 is still 1. Dividing by 2 gives r equals 1/2, which is 0.5. Comparing the two results, the radius of curvature is 0.5 near x equals 0, but 5.59 near x equals 1. This confirms the rule. The radius of curvature is smaller where the curve bends more sharply, and near the vertex of the parabola, the bending is sharpest. Now let us find the intrinsic equation for a simple curve, a circle of radius a. On screen, the circle appears first in 2 dimensions, then the same circle lifts into a 3-dimensional view, showing the tangent line rotating as it moves around the curve. For a circle of radius a, the radius of curvature stays the same everywhere, and it equals a itself. Since ρ equals ds by d psi, this means ds by d psi equals a, so integrating both sides gives s equals a times psi. To check this, let the tangent angle psi complete a full turn, so psi equals 2 pi. Then s equals a times 2 pi, which equals 2 pi a, and this matches the well-known formula for the circumference of a circle, confirming the intrinsic equation is correct.